Alright, so now we are going to start the exercises. You may be thinking, why a video? Why not a community post? Because that's where we have been solving all the exercises for quite some time now. I feel that, yeah, the community posts were okay, they were good because we were able to cover many exercise solutions at once. But that was also its bad point, which I felt later. It felt like we are just going through a lot of things very quickly without any explanation. Without any explanation means you have to read the solutions and no one is explaining the solutions to you. So I'm going back to making videos on exercises. So from now on, we won't see community posts on exercises, we will see videos. Okay, so let's see what this exercise set has for us. Here, of course, we are going to today see the first 12. And here, functions will be given, and for them we have to calculate the first derivative and second derivative, both. So the first one is this, y equals minus x squared plus 3. And the first few exercises we are going to solve in a manner which will show all the steps. That is, we will use all the rules, differentiation rules we have already seen, and we are going to be as detailed as we can. But after some exercises, we will be less and less detailed. It's up to you to decide how much you want to show. You can, if you want, you can just straight away write what the derivative is, if you have that amount of practice. But that, of course, comes with time. So let's see how this one goes. So we have to keep in mind, we have to find both the first derivative and the second derivative. So let's see the solution. We have, so first of all, naturally we will find the first derivative. dy dx, x is the independent variable, so although it's not mentioned, but obviously you will have to differentiate the dependent variable with respect to the independent variable. That is, you will calculate dy dx. And I said we will be as detailed as we can. So that means differentiating minus x squared plus 3. Okay. In the very next step, we write this. What have we used here? Here we have used the sum rule for differentiation. We know that this rule says that when you have two differentiable functions, then their sum is also differentiable. These are the two differentiable functions, minus x squared and 3, and the derivative of the sum is equal to the sum of the derivatives. But what do we do next? Well, minus x squared is minus 1 times x squared plus 0. This is the constant function rule or the constant rule. Whenever you differentiate a constant function, you get 0. It is that thing we are using here. Next, we use the scalar multiple rule. When you differentiate when you multiply a differentiable function by a scalar, by a real number, in this case it is minus 1, then the product is also differentiable, and the derivative of the product is that real number times the derivative of that original function. To put it less rigorously, to say it somewhat more casually, whatever constant you have here, that comes outside of the differentiation process. That's how you can remember it. And then we use the power rule here. So what does the power rule say? It says that the exponent comes down and it gets reduced by 1. So ultimately what you end up with is minus 2x. So that is the first derivative. Now we go for the second derivative. For the first few times, if this is the first time you are differentiating something, for the first few exercises, it's advisable to actually write alongside these steps which of the rules you have used. Say here within square brackets you write, I don't have space here, but you can write by the sum rule, by the constant function rule. Beside this step you can write by the constant multiple rule, then by the power rule, like that. Okay. So that later when you see your notes, if you are maintaining some kind of notebook where you are keeping some solutions, then you will better understand it when you see the which rules have been used again and again. Okay, 3 or 4 times you see like this and you practice, you will immediately know which one to use. It doesn't just come overnight, okay, that you read all the rules and you straight away you start solving them and immediately you know which one to use. It takes some time, no matter how easy something is. When you see something for the first time, it takes some time to get used to it. Okay, so that's why it's better to write them alongside. But anyway, let's now see the second derivative. Also, so you know the notation for the second derivative, it is this, d squared by dx squared. In order to really write what it actually is, you can write this step. For some of us, these things may seem like unnecessary, but actually they are necessary when you are doing it for the first time. It shows that you know what this means. So what is this? Minus 2x. Minus 2x is minus 2 times x. So again, just like this step, the constant comes outside. And then you are again using the power rule. The derivative of x with respect to x is 1, but how does that 1 come? Remember that here you have one exponent. 1 times x to the power 1 minus 1, which is x to the power 0, which is 1. So ultimately, you have minus 2. So the second derivative is a constant function. Remember, the derivatives we are talking about themselves are functions. It is that if you calculate the derivative of a function at a single point, then you will get a real number. Otherwise, you get a function. For example, the derivative of this function is this function, it's the function, it's not a single real number. Okay, so that was the first one. I am of course not going to solve all of them. Some of them I will just leave for you. But anyway, let's see what all the exercises are. For example, this second one is just like the first one. Y equal to x squared plus x plus 8. Okay, so that one was a polynomial, this one is also a polynomial. Polynomial functions are always differentiable. For this I won't write all the steps, I will simply write what the answer will be. I leave those details to you. This will be the first derivative, and the second derivative will be obtained by differentiating this again once more, and it will be 2. You may have noticed one more thing from this first and second exercise is that what was the polynomial in the first exercise? It was this, no? Minus x squared plus 3. The second derivative is constant. There also it is constant, minus 2. Here also it is constant, 2. But what is special about that? Note that both of these are quadratic polynomials. The exponent of x that appears in these polynomials, which is the largest, is 2. These are quadratic polynomials. When you differentiate a quadratic polynomial 2 times, you get a constant. If you differentiate a cubic polynomial, where you have x cube with non-zero coefficient, here also actually you have x cube, but that is 0x cube. Here the non-zero coefficient we have of x square minus 1, in this case that is 1. If you have a cubic polynomial, then the third order derivative will be a constant. You have to differentiate it 3 times to get to a constant, and after you get to constant you can keep on differentiating. We also saw when we were going through the theory in the last video that if you start with a polynomial and keep on differentiating it again and again, at one stage you will get constant, after that you will get 0, and all the higher order derivatives will be just 0, same thing. That's the nature of polynomials. The third one, here the variable names have been chosen something else, they are not y and x. The dependent variable is s and the independent one is t. 5t cube minus 3t to the power 5. Does not matter what name you use, after all it's also a function. Let's do this one. This type of variable names you may actually have encountered in mechanics, where t represents time and s represents distance. Maybe you have come across it. We have, so here also let me just supply all the steps and do it systematically. And again, do not make the mistake of writing dy dx. Now it will be ds dt. So if you really are interpreting, say in some situation, something is moving. It's just a hypothetical situation, okay? It may not actually occur. The distance that thing covers, say in meter, in t seconds is given by this relation, given by this formula. Say after t seconds of journey, this much distance is covered in meters. Then you know what this thing is. This will be the speed of that object. So that's how you actually need and have differentiation in mechanics. Instantaneous speed of the object. Okay, so this will be 5t cube. I carefully say speed and not velocity because you know the reason. These are scalar quantities. We are not talking about vectors. So what does the sum? Okay, and one more thing. Here, instead of using the sum rule, you can use the difference rule also to your advantage. So the minus will already be taken care of immediately. If you use the difference rule, then you have this. And then you use the constant multiple rule. So 5 comes outside, and here also 3 comes outside and gets multiplied with minus 1, becomes minus 3. And then you just have to use the power rule times. So the exponent will come first and then it will get reduced by 1. Oh, and one more thing, it's just a notational thing, but still it's a thing. When you write multiplication, see, often we do not use any symbol when writing the product of two objects. Say A and B are two numbers, their product is often written as AB. Whereas when you write the sum of them, you do use the plus sign. Here, however, very often we do not use the multiplication sign. We have two ways of writing the multiplication sign, your familiar cross or dot. But sometimes it's okay to not write. See, we follow this convention because it saves us from writing just too much. If there are two operations, addition and multiplication, and addition is always written, then you can afford to not write multiplication. Whenever there is nothing between two symbols, it's understood that it's multiplication. However, in situations like this, you cannot just write 53t square because then someone may interpret it as 53t square. So you use multiplication, but here is the thing. Don't put the dot here down below. That will mean decimal point. Put the dot here in the middle. If you do that, that will mean multiplication. That's what I wanted to say. Minus 3 times, here again 5 comes first and then the exponent of t gets reduced by 1. So we get 15 t squared minus 15 t to the power 4. So that is the first derivative. In our physical interpretation, that is the speed of whatever object is moving with that rule. Also, and now if you differentiate once more, physically you can interpret it as acceleration. But of course, this one involves nothing like that, just our imagination. So the second derivative will be this. So for that we have to differentiate this. I don't know much about mechanics, but I don't think anything will move like this, which will depend on the fifth power of time, third power of time. I don't know, but I don't think anything like this is physically there. That's why I said it's our imagination. Okay, so you use this expression for the first derivative, 15t square minus 15t to the power 4. Again we use the difference rule first. Let me calculate this, then I will say something about this entire process, something else which we haven't talked about yet. So 15 comes outside, t squared minus here also 15 comes outside, t to the power 4. And then the power rule will be used and we will get 15 times 2 comes first, followed by 3 with 1 exponent less. That means it's just t. Followed by t, sorry, I think I said 3. Minus 15 times, here 4 comes first, followed by t cube. So 30t minus 60t cube. Okay, so now I come to what I wanted to say about this entire thing that we haven't talked about yet. Recall the differentiation rules. These are some results, right? These are like some theorems. What does the theorem say? I mean, we have been using the various differentiation rules to calculate these derivatives. Take, for example, the difference rule. It says that when you have two differentiable functions f and g, then their difference is also differentiable. If I use the prime notation, this is the derivative of f minus g. The theorem says that it exists, and additionally it is the derivative of f minus the derivative of g. Now the way we have been doing this calculation, say you started with this s, this is our s, and we are using the difference rule. But can we use the difference rule? Look carefully at what the difference rule says. If f and g are both differentiable functions of whatever variable, independent variable we have, then f minus g is differentiable. If both of them are differentiable functions, then only the difference is differentiable. How do we know that 5t cube and 3t to the power 5 are differentiable? We don't immediately know this. Just think about it. We don't immediately know that 5t cube and 3t to the power 5 are differentiable. But then how are we using this difference rule? The answer you can see if you look at this expression. What we, however, know is that t cube is differentiable and t to the power 5 is differentiable. That we know from the power rule. And that is why, so the justification that we are able to use these rules comes from this expression. Because t cube is differentiable, so 5 times t cube is also differentiable by the constant multiple rule, and the derivative of 5t cube is 5 times the derivative of t cube. Okay, so that's how we know that 5t cube is differentiable. Similarly, because t to the power 5 is differentiable, 3 times t to the power 5 is also differentiable, again by the constant multiple rule. Now we know that 5t cube and 3t to the power 5 are differentiable, and that is why we can use the difference rule and by that rule, the derivative of this exists and is equal to this. You won't have to think of like this in every problem, but just telling you why we are able to use the rules in the first place. Is it justified? Yes. But the justification should lie like this somewhere in some step. And it doesn't necessarily start from here, the justification. Okay, so this is our, what is this? Third one, no? Yes. Okay, so let's now see what the fourth one is. Always never forget that whatever result, theorem, lemma, proposition, whatever formula, corollary, whatever you want to use, you want to apply somewhere, first of all make sure whether all the requirements of that result are met or not. If not, you cannot use it. Otherwise, you will get wrong results. Most of our mistakes in mathematics happens because we carelessly use results without knowing their range of applicability. Always just be careful about that. Next, the fourth one. Here again, some other variable name. 3 z to the power 7 minus 7 z cube plus 21 z square. Some people will call this letter z, okay. You call it whatever you want to call it. See, there is a purpose that the author is using different variable names just to confuse us, just to see if we really have got the idea or we get confused with the different names itself. This will discourage people from just mindlessly memorizing things like dy dx is equal to this, dy dx is equal to that. They will get confused whenever they see ds dt. But we know what they mean, so we won't get confused. Okay, so for this one, I won't really supply the steps. Let me write the answers instead. We will have this. (42z). That will be the first derivative of w with respect to z. And then the second derivative will be five Okay, so you write all the steps and see if you get these things. Next, the fifth one. The fifth one is, here you have a cubic polynomial. Here the degrees are really large. It's a 7th degree polynomial. Yes. So this one is 4 over 3 x cube minus x. For this also, I am not going to supply the steps. Instead, let me write the final answer. So we have again come back to y and x. And I think I can write the second derivative here itself. D squared y dx squared will be 8x. See if you get these expressions. Next 6. Y equal to x cube divided by 3 plus x square divided by 2 plus x divided by 4. Also, if you get a habit of differentiating these type of functions, do not attach too much, you just don't think like this, that always y will come with x, s will come with t. No such connection is there. You can have something, some other letter here as well. You can have s here. Okay, it can happen. Nothing essentially changes. It's just another name given to that same variable. It's like a person having multiple names. The person doesn't change, but there are many names. Okay, so let's do this one. We have dy dx equal to d dx of x cube divided by 3 plus x square divided by 2 plus x divided by 4. Okay, so you can see that there are 3 terms, but you can still use the sum rule, only its extended version. No matter how many terms are there, finitely many of course, you can distribute this differentiation over each one of them. Plus d dx of x over 4. And then naturally, because the way these things are going, we have so far seen only polynomial functions. First we use sum rule or difference rule, and then we take the coefficients out by the constant multiple rule. Here also we are going to do that same. And then we use the power rule. That's the natural sequence when differentiating a polynomial. Plus 1 over 4 d dx of x. So then if we use the power rule, what will be our first term? X cube becomes 3x square. We kind of start remembering this. We don't every time have to bring 3 down, and automatically it will happen. The moment you look at some such monomial, okay, when we say such an expression a polynomial because many terms are involved. If you have a single power of x, that's called monomial because one power. So the moment you see something like that, immediately you see 3x square. 3 and then 1 less. Plus 1 over 2, x square will be 2 and then 1 less. That means 1 here which you don't have to write. Plus 1 over 4. 1 times x to the power 0, so it's just 1. And you can see that there are some cancellations. So the expression becomes slightly simplified. Also, in place of also you can write next also if you want. Then the second derivative is d dx of dy dx you may have also uncovered another rule, or you have made an observation that whenever you differentiate a polynomial, the degree of the polynomial gets 1 less. That means your answer has degree 1 less than the original polynomial. This is a cubic polynomial, the derivative is a quadratic polynomial. Now we are again differentiating a quadratic polynomial, so the answer should be a linear polynomial, one where x itself is the largest power of x. And actually that's true. And it all happens because of the power rule. When you apply power rule, the exponent gets reduced by 1, that's why. So the extended version of the sum rule and then we are going to use the power rule. Luckily here we do not have, we have coefficient, but it's 1, so that we do not have to apply the constant multiple rule to take anything outside. We straight away apply the power rule, have 2x here, we have 1 here, and here we have 0, so it's just 2x plus 1. See, I said it will be a linear polynomial, so it's a linear polynomial. This type of problem can become quite complicated if you are given an unknown function, unknown in the sense that, see, so far we are seeing polynomials, so we know that they are differentiable. But if you are presented some very complicated function whose differentiability you don't really know about, then you have to be really very careful while applying the rules, because the rules are applicable only to combinations of differentiable functions. Okay, so that there you have to be careful, not exactly here. All right, so that was, which one have I done? Oh, this one, 6th one. So the next one is 7th one. And here we no longer have a polynomial. You see, this one is w is equal to 3 z to the power minus 2 minus 1 over z. This is not a polynomial. It, however, can be, I won't say reduced, but you can arrange things so that it will become a rational function. But that will not help us. This is the form in which we can differentiate most easily. But these are not polynomials. This is not a polynomial. But still, you can apply the difference rule, for example. That's what you have to apply first. But again, how? How do you know that 3z to the power minus 2 and 1 divided by z are differentiable? Well, that comes from the fact that they are themselves rational functions, quotients of polynomials, and such functions are differentiable at every point where the denominator is not 0. So, actually something else also should come with this function, a condition which says that z is not equal to 0. Z can be any real number other than 0. However, these exercises will test our knowledge on those differentiation rules. We are not exactly too worried about writing z not equal to 0 here. That's there in the background. Okay, it's understood. So you also, while solving these exercises, forget whether the functions are differentiable or not. Your main focus should be on applying the rules correctly. That's the purpose here. So we straight away just go for the first derivative. 1 + 2 × 3 + 4 + 5 + 6 + 7 + 8 + 9 + 10 + 11 + 12 + 13 + 14 + 15 + 16 + 17 + 18 + 19 + 20 + 21 + 22 + 23 + 24 + 25 + 26 + 27 + 28 + 29 + 30 + 31 + 32 + 33 + 34 + 35 + 36 + 37 + 38 + 39 + 40 + 41 + 42 + 43 + 44 + 45 + 46 + 47 + 48 + 49 + 50 + 51 + 52 + 53 + 54 + 55 + 56 + 57 + 58 + 59 + 60 + 61 + 62 + 63 + 64 + 65 + 66 + 67 + 68 + 69 + 70 + 71 + 72 + 73 + 74 + 75 + 76 And if you look carefully, this 1 over z actually can be written as z to the power minus 1. Why do we do that? Let's see. Let me first apply the difference rule with the condition that we know that this individual functions, this one and this one are differentiable. Are they differentiable? Yes. This comes from, again, that second form of the power rule where the exponents are negative. Such functions, such powers are differentiable at every non-zero real number z. Z to the power minus 2 and z to the power minus 1 are thus such differentiable functions. And because of that, by the constant multiple rule, 3z to the power minus 2 is also differentiable. And that is why we are able to use the difference rule in the first place. So everything is okay. In the next step, 3 comes out. Here, however, we can just write the derivative. Whatever rule we have here also the rule has exact same form. The exponent comes down, that means minus 1. And then you have to subtract 1 from the exponent. The exponent is minus 1, again minus 1. Okay? And a similar thing will happen here as well. Here also the exponent first comes down and then you subtract 1 from the exponent. This becomes plus z to the minus 2 minus 6 z to the power minus 3 plus z to the minus 2. Okay, so that is the derivative. Keep in mind, here we do not say things like this is a polynomial of degree minus 2. No, this is not a polynomial, so there is no question of any degree. But you can see one more thing, that we had minus 2 here, but now we have minus 3. Also, we have to next find the second derivative. So we have the first derivative here, minus 6 times z to the power minus 3 plus z to the power minus 2. So we first apply the sum rule with the understanding that it is applicable, and it is applicable. I mean, you know how. You don't have to say the same thing again and again. Plus minus 2. Excuse me. Okay, so the constant comes out. Minus 3. What will happen here? We have z to the power minus 2. That means minus 2 times z to the power minus 2 minus 1. Similarly here, minus 3 times z to the power minus 3 minus 1, and this one is minus 2 z to the power minus 3. 18 z to the power minus 4 minus 2 z to the power minus 3. So many negative powers. So obviously z is not equal to 0 in all of these things. A similar one is the next one, which I won't solve, but let me just show you the exercise. Here again we have gone back to s and t. This is also not a polynomial. Okay, so for this one, I won't even write the answers. Okay, it's left to you, and I won't do it. What is the ninth one? Note that this is also just like the previous one, it's not a polynomial. The ninth one is a mixture of positive and negative powers. Y is equal to 6x squared minus 10x minus 5x to the power minus 2. Although this part looks like a polynomial, but as a whole the function is not a polynomial because negative exponent is involved. This one also I won't do. Okay, it's left to you. You know what to do. You just have to apply the, you can do it in 2 steps. You think of it as the difference of 6x square minus 10x and 5x to the power minus 2. So there you apply the difference rule, and then once again you apply the difference rule to 6x square minus 10x. Then take the constants outside, use the power rule. Here you have positive exponents, here you have negative exponent, but the power rule has the same form of derivative. So that will give you the answer. And then the second derivative. Next, 10. Y equal to 4 minus 2x minus, again this one is similar. So this also I leave to you. 11 also I will leave. The 12th one I will do. R is equal to 1 over 3s square minus 5 over 2s. Same thing actually. This is 1 over 3 times s to the power minus 2 minus 5 over 2 times s to the power minus 1. This also you do. And finally, let's see the 12th one. R is equal to, well, divided by, here the independent variable is theta. We do have R and theta in a situation. You probably know about it. It's the polar coordinates. Just like we have the Cartesian system of coordinates for locating points in a plane, we also have the polar system of coordinates. There we have r and theta. We have, and in this one, I won't show all the steps. For example, let me straight away write dr d theta like this. I have already taken the constant out and I am differentiating because 1 over theta means theta to the power minus 1 minus 4 times theta to the power minus 3 plus theta to the power minus 4. So minus 1 comes in the front, makes 12 minus 12, and theta to the power minus 1 minus 1. That means theta to the power minus 2. Minus 4 times minus 3 will be plus 12 times theta to the power minus 3 minus 1 minus 4. And here if minus 4 comes in the front, then minus 4 times theta to the power minus 4 minus 1, that is minus 5. I don't advise doing like this now itself, okay, and particularly not for these problems. Whenever you have to differentiate something in some other context, say you have to find speed of something or acceleration, there you can do like this somewhat quickly, but make sure that you do not make any mistakes. And d squared r, d theta squared will be what? Yeah, now I am going to be even more sketchy. What will you do if you want to differentiate this? Obviously, you will apply the sum rule, difference rule, all those things, and the constants you will take outside. So essentially, you are just going to differentiate theta to the power minus 2, theta to the power minus 4, and theta to the power minus 5. So minus 2 will come in the front, will get multiplied with minus 12, and will give us plus 24 times theta to the power minus 2 minus 1, that is minus 3. Minus 4 times 12 is minus 48 times theta to the power minus 4 minus 1 is minus 5. Minus 4 times minus 5 is plus 20 times theta to the power minus 5 minus 1 minus 6. So this is the second derivative. But keep in mind, you don't do like this, not like this, not even like this. You really write all the steps and make sure that I also haven't made any mistake inadvertently. Okay. So these are our the first 12 exercises. So many others are there for us to solve. So we will do all of them slowly. And tomorrow also we have linear algebra. Okay, so we will go back to the actual thing in Jordan canonical form. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.